You will need your periodic table for today's notes, so please pause the video now and go get it if you don't have it out. Unstable nuclei that emit radiation are undergoing radioactive decay. In this section, we are looking at radioactive decay. So for a definition, radioactive decay is the process of emitting particles and energy from the nucleus of certain atoms. This results in the breakdown of unstable nuclei. A couple of terms right away are parent nucleus and daughter nucleus. The original nucleus is the parent. So the parent nucleus is the original unstable nuclei, or I'll say nucleus. And the daughter nucleus is the resulting product of decay. There are three main types of radioactive decay, and we're going to be looking at all three of them. First one is alpha, and the symbol for alpha. Second one is beta, the symbol's like this, and the third one is gamma. So alpha, beta, and gamma decay. In alpha and beta decay, the atom changes from one element to another. Alpha decay is the breakdown of nucleus, and it releases an alpha particle. Which is really a helium nucleus. And it consists of 2 protons and 2 neutrons. It's very weak, penetrating power, and as a result of alpha decay, the parent nucleus atomic number decreases by 2. So atomic number decreases by 2. And the mass number decreases by 4. So shown here in this general equation, which may be faded on your sheet because it photocopied weird, you might have to fill this in. We have the parent nucleus here, the mass number, switch back to pen, goes here. The atomic mass here when we're writing the symbols. So whatever the parent nucleus was, which is N, the symbol, and then you're going to have your mass number and your atomic mass. The daughter nucleus, the mass is going to be A minus 4 because the mass decreases by 4, and the atomic, I should say this is the atomic number. The atomic number would decrease by 2. And you also have to show that you've emitted a helium nucleus. So as an example of this, determine the nuclear equation for polonium-210 undergoing alpha decay. And we want to figure out what it changes into. Transmute means to change into. So we have polonium-210, and then we need to look up on the periodic table what its atomic number is, and we get 84. It's going to undergo alpha decay. So this would be the parent nucleus over here. And we're going to get a daughter nucleus. We know that the mass number will have to decrease by 4, so it'll be 206. the atomic number will decrease by 2, so we'll get 82. Then we just go to the periodic table and look up whatever 82 is, and we get lead, Pb, and we have to show a helium nucleus, because this is an alpha particle, being emitted. So we had parent nucleus, daughter nuclei, and I'm just going to label everything here. So this would be an alpha particle. You should note that the masses balance on both sides of the equation. So we had 210 as our mass over on the parent nucleus side. We have 206 plus 4, so the mass is the same. We had 84 over on the parent nucleus side, and we have 82 plus 2, so 84 over here as well. There is a practice question on your handout that isn't here, so I'd like you to pause this for a minute and answer the practice question. You should have got 241.95 changes into 237.73 Np and 4.2 He. Next type of radiation we're going to look at, next type of radioactive decay is beta. And this is when the nucleus breaks down and releases a beta particle, which is like an electron. It has a negative charge. And as a result of beta decay, one neutron transforms into a proton. And that proton stays in the nucleus, but the electron is emitted, and it's intermediate in penetrating power. You're going to have to know the relative penetrating powers of all three types of decay, and the beta is intermediate. The atomic number, because it's gaining a proton here, so the atomic number is going to increase by 1, and the mass is unchanged because it lost a neutron but gained a proton. So how this would look in the general equation is you would have the parent nuclei with whatever its mass and its atomic number. The daughter nuclei would have the same mass, but now the atomic number has increased by 1, and we're showing a beta particle being emitted. An example is if you were going to determine the nuclear equation for the beta decay of the isotope cesium-137. So we have cesium-137. Looking up on the periodic table, the atomic number here is 55. It's going to change into, so our mass stays the same, 137. Our atomic number increases by 1, 56. We look up what that is, barium, and we emit a beta particle. Please pause the video now and try the practice question. Oh, on the practice question, sorry if you just came back, I'd like you to do xenon 133 beta decay. So that would be xenon, it's Xe 133, 54. It's going to turn into 133, 55, which is cesium, and an electron. Third type of radiation is gamma, and this releases gamma rays. And it usually accompanies beta decay and alpha decay. Of the three, it has the highest penetrating power, so I'm going to write very high penetrating power. The atomic number and the atomic mass, the atomic number and the mass are unchanged. So atomic number and mass unchanged. And only energy is changed. So showing here the general equation, highlight it here, we have the parent nucleus, and this little star here indicates that the nuclei is excited, it has some extra energy, and we have the same nucleus after here, but it has missing that extra energy, and that energy is being given off as gamma radiation. So no mass, no atomic number, just gamma radiation. So an example for what that would look like, we have boron 12 undergoing beta decay to produce a excited daughter nucleus. So if we had boron 12 and boron's atomic number is 5, it's going to undergo beta decay. So the mass stays the same, the atomic number increases by 1, so we're going to get carbon, and we have to show that it's excited. And it was beta decay, so it lost that 1 electron. Then this carbon 12 nuclei is going to undergo decay to get rid of that extra electron. So we have carbon 12, 6. It's going to undergo gamma decay, so it's still going to be carbon 12 and 6, but it is losing a gamma particle. That's it for the notes that I've given you for today, so I'm going to stop this video here.